Chapter 8, Plug and Chug. So start out with number 38. Calculate the torque produced by a 50 Newton perpendicular force at the end of a 0.2 meter long wrench. So we're applying 50 newtons is the force. The lever arm or the moment arm, as I've talked about in class, is 0.2 meters long. So you just now recognize he's actually asking for the magnitude. He's not giving enough information to give for you to be able to give a direction for the torque, since torque is a vector. So he's asking for the magnitude, and so it's just going to be since the force is perpendicular to the moment arm, and because it states perpendicular, you're just going to multiply 0.2 times 50, which is 10 Newton meters. Now that Newton meters is a unit of torque. That Newton meters is not joules. Newton meters equals joules only when talking about work and energy. It is not joules when talking about torque, as will have been discussed in class by the time you probably have watched this. 39, calculate the torque produced by the same 50 Newton force when the pipe extends to a length of the wrench of 0.5 meters. Now it says the same force, so we can assume that it is still perpendicular to the wrench. The question is that force being pushed at the end of the 0.5 meters, or is it still being at the 0.2 meters? Two ways of interpreting that. So if it's still at the end, then the torque is 50 newtons times 0.5 meters, or 25 Newton meters. If it's still at the 0.2 meter mark, it is still the same torque as for the previous problem, number 38, so that'd be 10 Newton meters. Now the difference, even though the torque is the same, if you're applying at 0.2 meters in either case, then recognize there's a difference in the moment of inertia of the wrench, and so the angular acceleration would be different in the two cases. The longer the wrench is going to have a greater moment of inertia than the shorter wrench. So the more moment of inertia, more rotational inertia, the less angular acceleration. And generally when you're trying to rotate something, you want to push at the end. So pushing at 0.2 meters, you have potentially more control. However, you don't get as much impact. There's less influence. Number 40, calculate the tension in the horizontal string that whirls a 2 kilogram toy in a circle of radius 2.5 meters when it moves at 3 meters per second on icy surface. All right, so this thing is moving horizontally here in a circle. This is centripetal motion, and it is apparently attached to a string. It is a horizontal, and so the force is in the direction, the centripetal force is in the direction of the tension. Because F equals ma, if it's centripetal motion, acceleration is v squared over r. So the centripetal force, the total centripetal force is mv squared over r, and that point is just a straight plug and chug. The mass is 2 kilograms. I know that's the mass because of the units. The radius is 2.5 meters because it explicitly says so, and then it says 3 meters per second. That is a speed. Recognize the v in mv squared over r is speed. It is not velocity, because the direction doesn't matter for the speed for circular motion at a constant speed, but the direction of the force is pointing towards the middle of the circle, and no doubt my hand gesture is just really capturing that beautifully. Number 42, calculate the angular momentum of a person in the preceding problem. So in the preceding problem, 80 kilogram person sitting 2 meters from the center of a platform with a tangential speed of 3 meters per second. They could have just said speed of 3 meters per second instead of tangential speed. What he primarily wanted to differentiate was angular speed, which is not given here. So the angular momentum is mvr. It's basically r times the linear momentum, or mv. So technically r cross mv. So again, angular momentum is a vector, but he's actually asking for just the magnitude here. And since he is moving, so if you imagine a circle like this, he is sitting here as this turns. His tangential speed is perpendicular to the radial vector, so therefore it's just straight mvr. We don't have to worry about any angles or any lessening of the angular momentum because of that. And I guess sort of backing up, that's why tangential speed is important, because it is perpendicular to the radial vector. So we end up with mvr, and it's just straight plug and chug, 80 kilograms times 3 meters per second times 2 meters, done. And that is the plug and chug from chapter 8.